So, welcome back to particle physics and a standard model. This is lecture 34, and last time we had our first brush with symmetry breaking in the standard model. We saw a route that nature could have taken, but actually it did not, and we are seeing why it did not take that route. Okay. But to me this is a simpler way to think about symmetry breaking in particle physics. Okay. So, what did we do? We wanted the Higgs field to turn into some constant, right, and we saw that the way you break the symmetry is in the potential term of the Lagrangian, right, the potential meaning the scalar potential, and in this case we saw that if you are below the confinement scale in QCD, then since confinement happens dynamically without you having to do anything about it, right, that the strong force becomes stronger at lower energies, right. So, just like that the quarks, a quark and an anti-quark would pair up into a quark condensate, which is not a meson. You will see soon what a meson is. The quark condensate is more like a Cooper pair in superfluidity or in superconductivity, okay, and this degree of freedom now becomes a constant, this condensate, which is which goes as 3 powers of what is known as the pion decay constant, which is around 93 MeV, okay, and this is what happens on the way to confinement. So, just like that nature itself introduced a term in the Lagrangian for you, a term in the potential, which explicitly broke the electroweak symmetry that we wanted, the SU2 cross U1 symmetry, right. So, nature broke the chiral symmetry dynamically, and in that process it explicitly broke the electroweak symmetry for you. So, this we saw in the potential itself, which I am writing, which I am drawing for one component of the Higgs doublet field, okay, and we wanted to calculate what really was the expectation value of the field is at the minimum, right. So, also known as the vacuum expectation value. So, all you need to do is to find where the minimum is, and we are doing it in a simplified way where we now take only 1 degree of freedom from among the 4 and writing the potential down. And we saw that in the case where the mu square term times the expectation value, okay, is much smaller than f pi cubed, I can simplify the minimum condition to just 2 terms, right, and I am finding that in that case the expectation value goes as the pion decay constant itself, right, which is around 100 MeV, exactly 93 MeV in fact, but that cannot describe our real world, because we know that the mass of the gauge bosons that we get should be around 80 GeV, which is what we measure experimentally. The masses of fermions, some of the masses are indeed much bigger than 93 MeV. The B quark is heavier than a GeV, the top quark is around 173 GeV. So, this cannot describe the real world, okay. So, today now we will see yet another scenario within this framework of dynamical symmetry breaking, okay. We are still in round 1. Now, let me ask, what happens if, okay, let me call this case 1, case 2 is what? In the minimization condition, obviously it is the other way around. What happens if the first term and the third term, okay, if I retain these 2, that is case 2, okay. So, in that case what happens if I put in the minimization condition? So, I get the expectation value as f pi cubed over mu square, correct, and of course there is a lambda tilde sitting outside. To understand this better, I am going to write this as lambda tilde f pi squared over mu squared times f pi. Okay. So, why do I do this? Because this is a case where mu is so large, okay, that this term now is much smaller than 1, correct? In other words, V in this case is much smaller than f pi, right? So, this is even more manifestly not our world, right? This is this is again about 100 MeV. In the earlier case at least we got something close to MeV, close to 100 MeV, but this is much smaller than 100 MeV. So, this is also definitely not our world. Correct? Okay. So, then what other option do we have? This tells us that dynamical chiral symmetry breaking, right, is not electroweak symmetry breaking, in our world, which means we have to do something else. So, I am going to call this round 2, symmetry breaking round 2, okay. So, imagine now that you actually had, okay, mu square again much larger than other scales in the problem. For instance, mu square is still larger than f pi square, okay, so that you can now neglect the third term, okay. All right. So, literally this means another way to say it is this, okay. We will find in the end that the expectation value is indeed larger than f pi, so that these become equivalent, okay. See, earlier also I first guessed what the expectation value should be, that is why I wrote the condition this way. In the end that guess turned out to be right, right. In the end the expectation value was around f pi, so that this came out to be true, because indeed mu square is much smaller than f pi squared in this case, and everything worked out, right. Similarly, here I am going to take this limit where I am going to guess that the expectation value is larger than f pi, and we will find that it is true, okay. But not only that, I am also going to do something slightly odd. I am going to take mu square negative, okay. Then the potential, right, it is worth writing down the actual potential now without the f pi term. I can write it this way, correct, but that is nothing but h dagger h plus lambda h dagger h to the 4th, right. So, what happens if mu square is negative? How would the potential look like? So, once again I am going to draw a 2-dimensional projection of the potential, okay, but you have to imagine that it is actually there in all 4 dimensions in field space, okay. So, the potential, okay, I can now write as the absolute value, it should look like this. Would you agree? At 0 it should be 0, but if it had been positive I would have drawn a parabola that is upward facing, but since mu square is negative I will start with a parabola that is downward facing. Do you agree? And then what happens? As I keep going, the quartic term would take over, so this has to turn around, correct? Why? Because at h equal to infinity the potential is positive infinity, it is not negative infinity, right? So in fact because it is the quartic, the slope will get steeper, so let me as well draw it correctly, and it is symmetric. If I replace h with minus h, I am going to get back the potential, right? So I hope I am drawing this symmetrically. If I have not, imagine this is symmetric, okay, around v equal to 0 and h equal to 0, okay, around h equal to 0 in fact, okay. So that is the potential, okay. And if you solve for the minimum, what will you get as the vacuum expectation value now? You can easily do this and convince yourself that the vacuum expectation value is mod mu square over 2 lambda under a square root. Okay. Why mod mu square? Because if I just put a mu square, that is negative. I have explicitly taken mu square itself to be negative, right? Okay, good. Now where does this vacuum expectation fall on the diagram? Obviously somewhere here, right? That is the minimum, but you have to be a bit careful about this because now you have to imagine this in 4 dimensions, right? So what is actually going on is this is not just one, this is not just 2 dimensional, there is not just one point, there is in a sense a circle over here, okay, around which you generate this. It would be clear if I had written maybe if I just written the real part of h1 over here, it would have been even more clear. Why? Because there is another axis where you can draw the imaginary part of h1 also, but there is one more with the real part of h2, imaginary part of h2. So there is one big vacuum spanning all these fields, okay. But for now just imagine you have only 2 degrees of freedom, let us say you just have h1 and h2. In that case there is basically a circle down here on which all of which are at the same value of the potential, correct. In other words, right, there is no unique vacuum, okay, and that is the most important thing here, okay, because the possibilities, right, of what the actual vacuum expectation value could be, right, enjoy the symmetries. What do I mean by that? Enjoy the symmetries of the theory. See, on this potential, wherever I am on the potential, I still have all over the place, right, SU2 cross U1 symmetry, correct, and that includes the vacuum also, that includes this entire circle also, right. However, I cannot sit the field value when it actually does go to the minimum, cannot sit on the entire circle, correct, it can only go to some point on the circle, right. Do you agree? So, I am going to write that down, but the true vacuum, okay, that is the actual wave, right, necessarily breaks the symmetries because the system has picked one point at random. Okay. So, in other words, because it is forced to pick only one point among all the possibilities, you have broken your symmetry spontaneously. So, this mechanism is called spontaneous symmetry breaking. Okay. This is one of the, if not the most important concept in particle physics, but also in condensed matter physics. When you want to learn field theory and want to understand how a lot of phenomena happen, how a lot of phase transitions happen, how masses are acquired by elementary states, you need to digest the concept of spontaneous symmetry breaking. Okay. So, although your Lagrangian contained all the symmetries, in nature, again from the dynamics, okay, because the field value has to settle into some minimum, you have forced the field to go to one particular minimum. Okay. And although the minimum is not unique, it is a degenerate vacuum, right, you could only pick one point, right. So, that is what nature has done, and spontaneously it has basically picked one value. Remember, we wanted the Higgs field to go to some constant value, that is exactly what we have done. Spontaneously we have broken the symmetry. Okay. So, you might still wonder, if it had all these different possibilities, why did it pick only one, right? What is the real physical mechanism behind it? Okay. That just comes down to initial conditions. Okay. So, what do I mean? Let us see a simple example. Imagine I am making a pencil, okay, stand vertically, okay, on a level, this is level, this is supposed to be horizontal, okay, on a level table, let us say. So, the pencil is going to fall down, right, correct, but what direction is it going to fall down in? In some random direction, correct. But then think about this, the pencil actually had a 360-degree possibility, right. There was basically an entire circle around the pencil that could have been the direction in which it fell down, and every time you try to make it vertical, it falls down in some random direction, right, and if you do it infinite number of times, it will actually span the entire circle, correct. In other words, here also the minimum that the pencil could have fallen down to, right, the possibilities for the minima were actually degenerate, right. In other words, the possibilities for the minima actually enjoyed a circular symmetry, but the actual minimum to which the system goes is picked randomly, right. And why did the pencil fall in different directions in the different trials of this? Because of the initial conditions, correct. Because the way you actually held the pencil up vertically, there was some minute variation every time you held the pencil up, right, and that is ultimately what determined which direction the pencil fell in, correct. That is exactly what is going on here also. The field, right, started out in the early universe with some value, there were some minute variations, there would have been some very minute variation that would have decided its ultimate fate as the universe evolved, okay. So, this need not be wondered at too much, why, how exactly did the field pick one particular value, okay. So, let me clarify this with some more examples of symmetry breaking, spontaneous symmetry breaking, okay. There is one classic example of ferromagnets, examples of spontaneous symmetry breaking. Okay. So, how do ferromagnets work? So, the electron spins in a ferromagnet, right, when before it becomes a ferromagnet actually, right, I think it is called a paramagnet. Remember there are these domains of spins where they all align arbitrarily, right. But as you cool down, as the temperature of the magnet is cooled down, so let us say here you have high temperature in this phase, then what happens? Then you start aligning, at least within domains, you start aligning all the spins, right, and that is what gives rise to ferromagnetism, correct. But the alignment could have been in many different directions, right. There were many possibilities, the spins could have been aligned in this direction also, correct, but the system had to choose some direction, right, which depended on the initial conditions, correct. So, in other words, even though the Hamiltonian was invariant under spatial rotations, the ground state, okay, so though the Hamiltonian was invariant, the ground state picked one random direction, correct. Good. So, that is one physical example. Another is something we already saw actually, okay. Remember dynamical symmetry breaking that we saw for the case of chiral symmetry breaking, right, chiral symmetry breaking, that actually was a spontaneous symmetry breaking, okay. Why? So, let us go back here. Remember that as you cool down, you form these Cooper pair like states which are quark condensates, right. So, even the chiral symmetry, even the chiral Lagrangian actually has a degeneracy, okay, in the vacuum, and you had to pick one particular configuration of q bar q such that you formed such that you gave it a vacuum expectation value, one single vacuum expectation value, okay. So, even dynamical symmetry breaking is actually one case of spontaneous symmetry breaking, okay. Okay, very good. So, let me end this lecture with one physical meaning of this potential, and then we will talk about one particular observation that comes from this kind of symmetry breaking, okay, and then we will see the physical implication of this in the next lecture. Okay, I am going to talk about Goldstone's theorem next. Okay. But before we get there, remember the cosmological constant problem when we introduced quantum field theory for spin 0 fields, right. I said that when you write down a Lagrangian, right, you cannot help writing down a constant. We stopped writing this, but then it is always there, right, because it is not relevant for particle physics as such for doing particle processes, but every Lagrangian you write down for every field will contain this constant term, right, which when you write down the Hamiltonian it turns into a constant energy density across space and time, right, and across inertial frames also, correct. So, we had this, in fact let me just write it in the Hamiltonian itself. Okay. In the Hamiltonian we gave this a minus sign, and then we derived another term, right. What is that? The E naught, that is the 0 point energy, right. This was the bare cosmological constant, and sometimes the combination is called the effective cosmological constant or just the cosmological constant, right. Of course, there is a volume outside, okay, because it is not the Hamiltonian density, this is the Hamiltonian, okay. And look at the potential now, right. When the field goes and sits at the minimum value, right, it has basically, what has it done? In the potential, right, the potential has basically become, I am going to take it from here, it is just mu squared v squared plus lambda times v to the 4th, right. In other words, since the field has taken on a constant value, the potential has also taken on a constant value at the minimum, right. Correct. Put differently, this potential also contributes a constant energy density, okay. An even better word is to say uniform energy density across space and time basically, right. At every point in space you dump an energy density that corresponds to this, right. So, I can also write that term, correct. So, I am going to call it V pot to distinguish between the volume. So, the volume is just outside, pot is for potential, right, at the minimum. So, might as well call it that at the vacuum, correct. Put differently, this is also another contribution to dark energy, correct. So, we have now identified 3 contributions to dark energy, okay. So, once again let me emphasize that from a particle physics point of view, the mystery of dark energy is not really what it is, it really is how much quantity there is, that is the cosmological constant problem, right. So, we have identified, we have 3 ideas of what the dark energy is, because we have identified 3 different contributions coming from 3 different physical considerations, right. So scalar potentials, the 0 point energy of quantum fields and the bare cosmological constant, which you have to write down anyway. Okay. So, I will actually stop here, and in the next class we will make some observations about the massless modes that we produce in this spontaneous symmetry breaking, and what that actually implies for the masses of gauge bosons. Okay. All right. So, see you in the next class. Thank you.